Welcome to Central High School's IB Physics Unit 3. I am Mr. Tompkins, and we are going to discuss how objects behave when their temperatures change. The first lesson of this unit is called Thermal Concepts. In this lesson, we are going to discuss the basics behind temperature and thermal energy. Here are the objectives that you will cover in this lesson. You will receive a copy of these on your checklist. You can go ahead and read them now, pause the video, or you can just read them later. The ancient Greeks proposed that if you were to cut an object, more specifically a block of cheese, in half over and over again, you would reach a point where you could not do it anymore. They called the smallest piece of cheese an atom. Modern day science has produced a new version of the atom with protons, neutrons, and electrons. But for our purpose, using a simple sphere to represent an atom or molecule will be adequate for this unit. Elements are the basic building blocks of all matter in the universe. Each element has a different number of protons. The different amount of protons lead to drastically different physical and chemical properties of an element. Elements have different sized atoms, which lead to different masses for each element. Notice the difference in size of the oxygen atom versus the xenon atom. So here's the oxygen atom, and right down here is the xenon atom. They are significantly different in size. When two elements combine, we get a new compound or a molecule with different physical and chemical properties of the original elements. Here we have two hydrogen atoms and one oxygen atom. Hydrogen and oxygen are both gases at room temperature. But when we combine them, we get water, which is a liquid at room temperature. The periodic table contains important information that we will need to use for this unit. The first one is the atomic symbol. This designates the element that is being represented. Some of these are easy to figure out, such as carbon, which has a C, or oxygen, which is an O. Some are difficult, though. Gold, which has an atomic symbol of Au, and sodium, which has an atomic symbol of Na. We also get the atomic number. This describes how many protons an element owns. This is the only determining factor when categorizing elements. And then we have the atomic mass. This is the sum of the atoms, protons, and neutrons. One proton has a mass of one atomic mass, and one neutron has about the same mass as a proton. It's a little bit more because it contains both a proton and an electron. The electron's mass is so little compared to the protons, we don't include it in the atomic mass. But how can we have fractional atomic masses? We can't have parts of protons. We can't have parts of neutrons. Instead, it has to do with the average atomic mass of the element. Most elements have more than one isotope. This means that there are different versions of an element with different amounts of neutrons. The atomic mass is okay when we're talking about the microscopic universe, but with thermal physics, we are going to look at amounts that are much higher. We need to convert the number of atoms in a substance to our SI units of mass, the gram and the kilogram. We use a constant called a mole. A mole is just a quantity that relates the atomic mass of an object into grams. A mole of any element or molecule is always going to have 6.022 times 10 to the 23 atoms in it. This is also called Avogadro's number. But the mass of the mole will depend on the atomic mass of that substance. 1 mole of carbon is going to have 6.022 times 10 to the 23 carbon atoms in it, but it's only going to have a mass of 12.01 grams. Whereas 1 mole of platinum is going to have 6.022 times 10 to the 23 atoms in it, but it's going to have a significantly larger mass than the carbon at 195.08 grams. So here's an example problem of calculating using the molar function. So how many atoms are in 18.9 grams of selenium? Well, let's research the information needed. So here's the selenium block from the periodic table. First, we'll start by figuring out how many grams are in 1 mole of selenium. 1 mole of selenium is 78.96 grams. Then we create a conversion factor, convert grams to atoms. Our conversion factor states there are 6.022 times 10 to the 23 atoms of selenium for every 78.96 grams of selenium. The last step is to multiply the original amount of selenium to our grams to atom conversion factor. And for that, we get that there are 1.44 times 10 to the 23 atoms in 18.9 grams of selenium. Here's another example problem. The density of iron is 7,874 kilograms per meter cubed, and the mass of a mole of iron is 55.85 grams. What is the volume of 2.3 moles of iron? Well, we know that density is going to equal mass divided by volume. And so if we rearrange that using algebra, we know that the volume is equal to the mass divided by the density. What we need to do is we need to figure out what is the total mass of 2.30 moles of iron. So we take the mass of 1 mole of iron and we multiply it by the number of moles. And that will tell us the total mass. So the mass of 1 mole is 0.05585 kilograms. Notice I had to convert that into kilograms in order for this to work. And then I'm going to multiply that by 2.30 moles, and then I will divide it by the density, which is 7,874 kilograms per meter cubed. And I get that the volume of 2.3 moles of iron is 1.63 times 10 to the negative 5th meters cubed. Internal energy and friction. This block that we see on the table here is given an initial velocity to the right. The block then slows to a stop. So the block started with kinetic energy, but ended with no energy. Where did it go? The energy is lost due to friction between the block and the table. We have another scenario, and in this time, we are going to apply a constant force on the block to the right, which means we are going to do work on the block. But the block remains at a constant velocity. This means the block is not gaining any new energy from my work. So where is the energy going? And once again, it is lost due to friction. So let's talk about what is friction. Friction is an opposing force between two surfaces that want to slide across each other. It is caused by imperfections at the atomic level of the two surfaces and the electrostatic forces between their atoms. These forces on the atoms/molecules increase the motion at the atomic level on both surfaces when they slide past each other. More movement in the atoms/molecules results in a higher temperature. Think of friction as a force whose work is always transforming mechanical energy into thermal energy, which we will also call as heat. Here we have two surfaces sliding past each other. Notice the microscopic imperfections in the surfaces. If I were to rub the yellow surface onto the green surface, you will see a friction causing the atoms to push on each other and vibrate more rapidly. This is an increase in the temperature of the atoms. The more I rub, the faster the vibrations become until I cause the surfaces to heat up so much they melt and we lose atoms to the environment. And so we'll see that these atoms get sheared off and they fly away because they have melted. So it's sort of like rubbing two pieces of plastic together until they melt. And then whenever I separate them, you'll notice that the temperature goes down and the atoms themselves stop vibrating as much. So how much energy goes into friction? So here's an example problem. We have our first scenario where the block has an initial velocity and it slows due to friction. All right, the block, we're going to give it as a mass of 2.5 kilograms, and the initial velocity is going to be 3.0 meters per second. Well, we know by conservation of energy that the work is going to be equal to the change in the kinetic energy, or the change in the energy. And in this case, the work done by friction, remember how we said it is a mechanical, it is a force that transforms mechanical energy into heat. We are going to give it the symbol Q, which stands for thermal energy. So Q is thermal energy. And so this is going to equal our change in the kinetic energy, which is what the block had at the beginning, and then it no longer has at the end. And so we have the equation for conservation of energy saying that the heat is going to be equal and the difference between the final kinetic energy and the initial kinetic energy. If I were to plug in numbers here, we notice my final velocity is 0, so that whole term goes away. And so I get negative 1/2 times 2.5 times 3 squared. And I get that the heat taken, or the heat inside due to friction, or the transfer of energy from mechanical energy into heat energy, is negative 11.25 joules, or with significant figures, negative 11 joules. So that means that friction has taken away 11 joules of energy. And so now both surfaces have 11 joules more internal energy than what they started with. If we look at the next scenario where I'm doing work on the block, but the block isn't gaining any kinetic energy. In other words, I'm applying a force to the block, but it isn't speeding up. There it goes. I'm going to say that the force that I apply to the block is 4 newtons, and the displacement of the block is 3 meters. Once again, the conservation of energy equation, which says that work equals my change in my energy. And so the total work done is the work by us plus the work done by friction, or the heat that is being transformed from the mechanical energy. And because the energy is not changing, in other words, the amount of energy I have at the beginning is equal to the amount of energy I have at the end, then I know that the work, or the heat, is equal to the opposite of the work that we complete on the block, or the work equation, which is the force that we apply times the displacement times the cosine of the angle between the two vectors. The angle between the two vectors is 0 degrees, and so whenever I plug this in, I get that the heat, or the amount of thermal energy that has been transformed from mechanical energy, is 12 joules. So let's talk about what is temperature. Temperature is a measure of the average thermal energy, or the average kinetic energy of the particles in a substance, in the object. Notice how I did not say it means hot or cold. Hot or cold are relative terms based on our own perceptions. We measure temperature using a thermometer, and the units of temperature is degrees Celsius or Kelvin. Now, the way that these two are related is that 1 degree Celsius equals 1 Kelvin. The only difference is that in order to convert from Celsius to Kelvin, all we have to do is take the temperature in Celsius and add 273 to it. And then that will give us the temperature in Kelvin. So carbon, that is, or an object that is 40 degrees Celsius, has a Kelvin temperature of 313 Kelvin. An object that is negative 215 degrees Celsius has 58 Kelvin. So here's a hot and cold experiment. Try this at home. But this will help you realize that hot and cold are just merely your perceptions, and they're not really fact. So please try it. All you have to do is pause the video and conduct the test. It'll probably take you about maybe 10 minutes, and then you'll understand that we won't describe temperature in the forms of hot or cold. There are 3 phases of matter: solids, liquids, and gas. There is a 4th phase of matter called plasma, but individual elements are indistinguishable at this point because during this time, electrons and protons are being knocked out of the atoms themselves. And so the matter itself has been transformed into energy. So for our thermal physics, we will talk about these 3 phases of matter: solids, liquids, and gas. Properties of solids. Solids have a cooler temperature than all other phases of matter. They do not have enough thermal energy to stretch the bonds between their molecules. In this water, which is in the tank here, the white hydrogen atoms are attracted to the orange oxygen atoms in their other molecules around them. This creates a rigid lattice that holds the water in a solid form. Solids have a finite shape and volume, so their shape and volume are fixed. Properties of liquids. Liquids are warmer than solids but cooler than gases. They're more like the transition phase between the two, between solids and gases. The molecules have enough energy to weaken the bonds between other molecules, but not enough to totally break free. Notice how the white hydrogens are no longer attracted to the orange oxygens. They are allowed to bounce around. You will see in this simulation where one molecule of water is launched beyond the proximity of the other molecules. This is not an artifact of the simulation. This is actually how water evaporates at a temperature that's below boiling. And you can see this, and we'll watch it. It's this one out here. It's going to get hit again, and it will get launched out here, and that's evaporation. So this molecule that's leaving, that is how water evaporates. Liquids have a finite volume. Their volume stays the same, but their shape is not constrained. They take the shape of whatever container they're in. Now we're going to talk about the properties of gases. They are warmer than both solids and liquids. The molecules have enough energy to break the bonds between each other, which sends them flying off at a constant velocity until they run into another molecule. Think of a heavy ball on the end of a thin string. You throw the ball at increasing speeds. The first couple of times the velocity is so small the string is able to pull the ball back. But once the ball gets moving fast enough, it is able to break the string and keep going. Gases' volume and shape are not defined. Their volume can be large or it can be quite small. It depends on how much we compress them. And their shape usually takes the shape of whatever container they're in, or if they're in a big room, it will diffuse out and fill up the room. Heat transfers. When two objects have different temperature, heat will flow from one object to another. Heat always moves from the object with the higher temperature to the object with the lower temperature. There are three ways energy can move, or heat can move. The first one is conduction, which is where the atoms of two objects are in direct contact while the heat is transferred. We have convection, which is the movement of heat by a fluid. Think of your home furnace pumping heat through the air, and then the reason why you feel warm is because that warm air is touching you. You can also see this in boiling water. There are currents that you can see when you look down in there of the water whenever the bubbles come up, and then which produces the heat and moves the heat around inside the water. And then the third type, or the third way that energy can move, is radiation. This is the heating of an object by electromagnetic waves, sort of like a heat lamp that you would see at a restaurant, or even our sun. There is nothing in between us and the sun, so the only way we get heat from the sun itself is by radiation. Conduction is the only transfer method that we are going to worry about in this unit. And so here's a short video discussing conduction.
Conduction. If you stir a boiling liquid with a plastic ladle, after a few moments, the ladle will become quite warm. The same will happen with a wooden ladle. And a ladle made of metal can even become too hot to handle. This is because the heat from the boiling liquid is able to travel up the length of the three ladles, quite slowly through plastic and wood, and very fast through metal. But how does heat manage to do this? How does heat travel through things? Well, when the hot liquid heats up the end of each ladle, its molecules, or in the case of metal, its individual atoms, start to vibrate more rapidly. And when the heated molecules, or heated atoms, vibrate faster, they start bumping faster and faster into their slower neighbors, causing them to speed up in turn and bump into their neighbors. and so on all along the ladle. In this way, the increased speed of vibration, and therefore the heat, is passed on from molecule to molecule, or from atom to atom. It's like a row of dominoes knocking each other over. And this domino effect, which leads or conducts heat through any substance, is called, naturally enough, conduction. Non-metals such as wood and plastic conduct heat quite slowly. They are bad conductors of heat. In contrast, all metals conduct heat very rapidly. They are good conductors of heat. That's why the witch with a metal ladle got burned.
Heat flows from higher temperatures to lower temperatures. That's what we discussed in the last slide. It continues to do so until the objects reach the same temperature. This is called thermal equilibrium. Thermal equilibrium is when two objects of different temperature are placed next to each other and their temperatures become the same through conduction. This brief animation illustrates the concept of thermal equilibrium. We have two objects, objects A and objects B. Their initial temperatures are different. Object A is 50 degrees Celsius, object B is 25 degrees Celsius. As we look, we notice that the energy is being transferred from object A into object B, and so object A's temperature is decreasing while object B's temperature is increasing. And thermal equilibrium is at 38 degrees Celsius. And now to recap. Elements are the building blocks for all matter in the universe. Molecules are made up of more than one atom. The mole is used to convert from atomic mass into grams. 1 mole is 6.022 times 10 to the 23 atoms, and 1 mole of an element equals the atomic mass of that element in grams. The energy lost due to friction is converted into thermal energy, or heat, which is given the symbol Q. Temperature is measured by a thermometer and is in degrees Celsius or Kelvin. There are 3 phases of matter. You have solids, which have a finite shape and volume, liquids, which have a changing shape but a fixed volume, and gas, where there is no fixed shape or volume. Heat is transferred through a process called conduction, where atoms of 2 objects bounce directly off of each other. Heat always transfers from objects with higher temperature to objects of lower temperature until they reach the same temperature. This is called thermal equilibrium.